When you pull up to the pump, you often have a choice between standard gasoline and E85. These are chemically distinct liquids. Standard gasoline is derived from crude oil, while E85 is a blend containing up to 85% ethanol, a renewable alcohol typically produced from crops like corn or sugarcane. Because of that chemical difference, they require different amounts of oxygen to ignite. Gasoline has a stoichiometric ratio of 14.6, meaning it needs 14.6 parts of air for every part of fuel. Ethanol's ratio is much lower, at just 9.0. If a vehicle engine calculates the air intake for gasoline, but the fuel injectors spray ethanol, the ratio is incorrect for the chemistry. The engine will choke, misfire, or stall out. Yet flex fuel vehicles are engineered to run on either fuel, or any random blend of the two you happen to create in your tank. This suggests the manufacturer installed a specialized sensor inside the fuel line to directly analyze the liquid's chemical makeup. In reality, physical ethanol sensors are prone to degradation and add significant cost to the vehicle. Consequently, most manufacturers leave them out entirely. When you drive away from the pump, your car has no data on what you just put in the tank. The engine is forced to adjust its precise internal timing based on data it cannot verify directly, balancing the combustion process without ever physically sampling the liquid in the tank. The adaptation cycle begins as soon as the vehicle's computer detects that the fuel level has increased. Lacking a direct measurement of the new blend, the computer issues a blind feed-forward command. It operates on the assumption that the new fuel is the same blend as whatever was previously in the tank. It injects that unverified mixture of air and fuel directly into the engine's combustion cylinder and immediately ignites it into a bright flash. To figure out if that initial guess was correct, the system relies on the exhaust gas oxygen, or EGO sensor. The EGO sensor is separated from the raw fuel lines, located all the way down in the tailpipe. By analyzing the waste gases left over after the combustion is finished, the vehicle's computer can mathematically reverse engineer exactly what occurred inside the cylinder. This diagram shows the system's control loop. The EGO sensor measures if the combustion was too rich, meaning it lacked oxygen, or too lean, meaning it had excess oxygen. If the burn is off, it sends a feedback signal to the main engine control unit. Receiving that signal, the computer realizes its initial guess was wrong. It adjusts an internal dial, changing its assumed stoichiometric air-to-fuel ratio, perfectly correcting it using the exhaust. That updated ratio is then plugged directly into a calculation formula. The formula outputs the exact volume percentage of ethanol currently flowing out of the tank. This algorithmic workaround loops continuously, updating the engine's calibration maps on the fly without the driver noticing. The vehicle identifies the chemical makeup of a mystery liquid just by reading the results of its combustion. Clever software loops have completely replaced a fragile piece of physical hardware. This indirect measurement introduces a new vulnerability. The math only returns a true result if every other variable in the equation is absolutely accurate. To correctly reverse engineer the fuel from the exhaust, the computer must know exactly how much air originally entered the engine. For that, it relies on a mass airflow, or MAF, sensor at the intake. A paper from researchers at the University of Michigan and Ford Motor Company analyzed the precise sensitivity of this specific control loop. This chart shows their findings. If the mass airflow sensor drifts by just 5%, the cascading math spikes the estimated ethanol calculation by 30%. A 30% miscalculation blinds the computer again. It issues incorrect commands, resulting in a poorly running engine. Removing a physical sensor trades hardware durability for software sensitivity. The vehicle becomes a delicate mathematical ecosystem where a slight measurement error at the intake results in a total failure to calculate the chemistry at the tailpipe.